Is it okay?
Yes.
Okay. So first of all, let me thank Andrea and Lara for organizing this workshop. I organized my talk into these three parts. I will give a very brief introduction, of course, not exhaustive on GRBs. And then I will try to explain and show what we know about the spectral properties and how we can what we can understand from these properties in terms of the emission mechanism regulating the prompt emission. And as Lara said, I will show some preliminary results about Hermes expectations and contributions to some of these topics. So, okay. So a gamma ray burst is a prompt flash of high energy photons. We know since 1997 that this emission is accompanied by what we call the afterglow, which is a long-lasting emission, which decays as a function of time and is observed all over the electromagnetic spectrum. One of the differences between the prompt and the afterglow is maybe the fact that the prompt is variable on a second or sub-seconds time scales, whereas the afterglow decays more smoothly. We also know that gamma ray burst comes into two classes divided based on their observer frame duration, the short and the long. They have differences and similar properties. For instance, if we look to the isotropic equivalent energy, we see that it is spread all over almost 8 orders of magnitude, with maybe short ones being a little bit less energetic than long ones. For what concerns their distance, the short bursts are localized at relatively closer distances with respect to long ones. These ingredients, of course, together with direct studies and detections of their progenitors, meaning the identification of supernovae in association with long GRBs and the famous 1708-17 event for short, led to our present understanding, the possibility that long ones are produced by the core collapse of massive stars and the short ones by the merger of compact objects in the form of two neutron star or a neutron star and a black hole. The endpoint of their progenitor evolution seemingly is the formation of a compact rotating central object surrounded by a torus, which is able to power two relativistic jets. So let's say a very pictorial way of describing what could be a GRB is shown here, where you see we think we have some energy extraction from the central engine, which is collimated into a narrow jet, which accelerates and is opaque in this initial phase up to the point when it becomes transparent. And eventually the radiation which is trapped within it is left free to be released, producing a nearly thermal spectrum. At more or less the same distance, the dissipation might be regulated by the formation of shocks, which are called internal shocks, which accelerate the particles and amplify the magnetic field, producing emission through synchrotron. And again, it is synchrotron, the emission mechanism, and again, shocks, the dissipation mechanism, regulating the dissipation of the bulk of the energy when the jet is decelerated by the interstellar medium, producing the afterglow. Now, when we think about the prompt emission of gamma ray burst, I would like to show it through this example. Is a very famous old gamma ray burst. Here you see the photon spectrum, which is a featureless broadband spectrum extending over 3 orders of magnitude. It can be described by a low energy power law, a high energy power law connected smoothly at a break. When this is transformed into the nu-F-nu SED representation, this spectrum has a peak, and statistical studies on bursts detected by different instruments in the past, up to the present, depicted the fact that we have typical values for instance, for the slope of the spectrum at low energies, the so-called alpha photon index, centered around more or less around 1. We have a typical slope for the high energy power law, and the peak of the nu-F-nu spectrum is typically located at around a few hundred keV up to 1 MeV or so. when going back to short and long GRBs, the main differences that we can see between these two sources from the spectral point of view related to the prompt emission is in the low energy part. Because if we look to the distribution of the low energy photon spectral index as a function of duration, so short and long here highlighted with different colors, we see that short GRBs have a harder low energy spectral slope compared to long ones, and instead they are almost similar if properly correcting for the redshift effect, which is affecting their peak energy. Now, this kind of plot is very instructive because it can be used to let's say, test or discuss what could be the prompt emission mechanism regulating the prompt emission in GRBs. If we think, as I said, that this is related to synchrotron emission, then we should think about the fact that at the shock, we have that electrons are accelerated into a non-thermal tail, which has an energy distribution, which is gamma to the minus p. And these electrons then cool and lose their energy. And the two main mechanisms related to synchrotron is synchrotron itself and inverse Compton emission. So it was realized back in 1999 that if we compute the cooling time scale, which is related to the energy density of the magnetic field and the energy density of the radiation field, we have that for typical values of the magnetic field, which should be of the order of 10 to the 7 Gauss in the emission region of the internal shocks, and the size of the emission region, which is inferred from the variability time scale, we should expect, or we should find that this this cooling time scale to be extremely short. Typical value 10 to the minus 8 seconds. So this means that if we take a snapshot of the prompt emission of a gamma ray burst, we should see the spectrum produced by a totally cooled electron population. In terms of observable, this spectrum should be characterized by a high energy power law, whose slope is not fixed, or at least is regulated by the slope of the energy distribution of the injected electrons, so the p-value. But below this break here, the spectrum should follow this line, the violet one, having a typical slope minus 3/2. Of course, if you compare with the plot here, you see that the majority of GRBs are inconsistent with this slope. This was claimed back in 1998 by Robert Preece as the inconsistency of the observations with the theory. And this represented for more than 30 years the problem of synchrotron emission as the explanation for the prompt emission in GRBs. So there was this tension between observation and theoretical predictions. The situation changed, started to change, I would say 3 years ago, thanks to a kind of way of looking at, in a different way probably, to even archival data. So the first evidence came out with the works by Goro Ganesian, that was at that time a PhD student at CISA, now he works at GSSI. And his two papers, one in 2017 and the other one in 2018, he analyzed the GRBs detected by SWIFT. The aim of this work was to see how the spectrum behaves when we extend the prompt emission analysis of the spectrum down to the soft X-ray band. And what Gore found in a large fraction of the analyzed burst is that in addition to the typical nu-f-nu peak that you see here, the spectrum presents a break at lower energies. Interestingly, the slope of the spectrum, the photon slope, this is the nu-f-nu, between the peak and the break, so this part here, is clustered around the typical value, which is minus 3/2. And the spectrum below the break is minus 2/3. These are the typical slope for the cooled electrons distribution, and this is the single electron value. So this kind of analysis, however, required the fact that XRT monitored whatever it could of the prompt emission. So in general, the selection was picking out bursts which were quite long in duration, or bursts in which the trigger of SWIFT happened on a kind of precursor in order for the satellite to slew and have XRT following the main event, which are, let's say, a small fraction within the population of GRBs, at least 10% in the long and something smaller for the short. But the evidence that this kind of break was present also in other bursts, not selected only with this criterion, came from the analysis, for instance, performed by Maria Ravasio on bursts detected by Fermi GBM. She's now a PhD at the University of Bicocca, and in her works of 2018 and 2019, where she analyzed 10 long bright GRBs detected by Fermi and 10 short bright GRBs detected by Fermi GBM, what she found is that for the majority of long GRBs, the shape is something like this. So there is clearly the evidence of a break, in this case around 100 keV, so at higher energies with respect to those found by Oganesian. And the slope below the break and between the break and the peak are consistent with synchrotron values. And the ratio between the break and the peak is 1/10 here compared to 1/30 that was found instead in the previous works. Interestingly, she found that no short GRB has a break, and the slope below the peak, in this case, the only peak present in the SED, was minus 2/3. And this value is indeed the value that in long is present below the break, as if short GRBs are those cases in which the break is close to the peak. Now, these kind of results were based on, let's say, reanalyzing or analyzing bursts with an empirical approach, meaning using empirical functions that were fitted to the data with, let's say, a model-independent approach. However, also direct fits of the synchrotron model to the GRB spectra were performed, again, in the last 3 years. And these are the works that found consistency of the data with a proper fit of synchrotron model. So it's a model that is derived by solving the continuity equation for the emitting electrons and applying the synchrotron formula. So I'd like to show one burst as an example of this kind of approach that was analyzed in this paper by Michele Ronchi, at that time a master student at the University of Bicocca and now in Barcelona. This burst is a very famous one among the brightest events detected by Fermi, and is famous also for its being detected also at very high energies. So in GRB 1708-20b, what was found is that the spectrum is very well consistent with a synchrotron model. And the power here is that directly from the fit, one can get the physical parameters at the emission region. Specifically, the cooling frequency in this case is at 100 keV. The peak frequency, which in the synchrotron interpretation corresponds to the minimum energy of the injected electrons, so the start of the power law tail, is 2 MeV roughly, and the value of the high energy tail of the spectrum corresponds to a P, so the slope of the electron accelerated at the shock, which is quite soft. Let me say that if we take all these results together, the main, I would say, outcome, there are many things we could discuss, but the main point, which I think is extremely important, is the fact that they all, let's say, point towards having this break close to the peak. So the cooling frequency close to the peak frequency. And this is the main point, the main result. What does it mean, or how can we interpret that? Since again, we go back to the radiation losses, which are regulated by synchrotron and inverse Compton, which depends on the energy density of the magnetic field of the radiation, and the dependence they have on the magnetic field itself and on the size of the emitting region, what comes out is that in order to have the cooling frequency at keV energies, we must require the cooling timescale of the electrons to be quite large. And therefore, as a consequence, to have a region where the magnetic field is small and the dissipation radius is large, where the dissipation happens. So with these, let's say, typical values, these one I'm quoting here are derived by an analysis performed by Oganesian over a larger sample of bursts, but similar results are obtained in this work by Ronchi and also in the others I'm citing here, all point towards the fact that in order to explain these new results, we have to call into play electrons that radiate with a moderate cooling efficiency. So what is called the different terminology, moderate fast cooling or no cooling or so forth. So what is the point here? I think the point is that after more or less 30 years of investigation and debate about the possible outcome to solve the inconsistency of the observation with theory, I think we have done an important step forward in understanding that indeed synchrotron can be the way out to solve this problem and can be the emission process, despite the fact that some of the parameters of the emission region are really puzzling, and possible ways out in order to justify and explain such, let's say, issue, making, I mean, the solution could be having a magnetic field which is not that small, contrary to what can be derived from these results, and the dissipation regions, which is smaller because it raises the issues of the variability timescale of the prompt, which is very small. Could be, for instance, if you are curious, you can go and look to this paper by Ghisellini, where, for instance, protons are proposed as a possible solution to these very low values of these parameters, and a discussion of possible alternatives are also given. Now, I move to the next to the third part of my talk, gamma ray burst detection rates. So with Lara and Fabrizio and Pepe Di Lillo, we have been working on, of course, one of the first things we try to explore is what will be the detection rates of GIBs by HERMES. Here, let me make a point. I hope I gave at least the ingredient to understand that gamma ray burst detection rates depends, of course, on the instrument that you are building, but also on the properties of the population of sources that you are exploring. And it is the interplay of these two that determines the final detection rates. You can understand this, for instance, from this simple plot, which shows the GLBs detected per year, so the rate of long and short GLBs detected by famous detectors. And of course, the ratio, the differences between among detectors and the differences between, for instance, short and long within a single detector are, of course, the result of the interplay of these two groups of ingredients. On the one side, the GLB intrinsic properties, meaning their luminosity distribution, their redshift distribution, the SED, which can be different between short and long, as I showed, and their duration. On the other side, the instrumental properties, generally speaking, the energy range where the signal is accumulated and the corresponding background, the field of view, and the duty cycle. So the approach that we decided to take here, it's a population-based approach. What does it mean? It means that we based, let's say, the detection rate estimates on populations or describe the intrinsic properties of GRBs, both of the long and of the short classes. And there are different ingredients. The leading ones are the luminosity and energy functions that describe the population and their cosmic rate distribution. These are not, of course, free functions, but they are derived and calibrated in order to reproduce the samples of GRBs that we have been detecting so far. So once we have built this kind of machinery, we have somehow the iceberg, which is below the surface. And now we can use it to predict, according to the density of the liquid where it is immersed, what will be the tip that we will explore. Meaning that with Hermes instrumental parameters set in, we can derive the Hermes GRB detection rates. This kind of approach is, I think, has some advantages, such as the fact that selection biases are better under control with respect to, let's say, simple extrapolation from the tip of the iceberg that we have been exploring with present missions. And I think another advantage is the fact that the same kind of approach based on the same population has been used so far for estimating other detection rates by other instruments or missions, such as CTA and Theseus. So it's very useful to explore the synergies if we want. The results were anticipated by Fabrizio. So these are the parameters that we take into account. We work with both the S and X detector, meaning having two different energy bands. We take into account the dependence of the effective area with the angle with respect to the satellite sorry, to the detector normal. We set in a threshold for the detection larger than 5 sigma. We take into account the duty cycle. We work with the peak flux of the fluence. And these are the numbers, more or less. For the total one, you see that we have a detection rate between 50 and 150 for long and around 14 for short GRBs per year. The large number here, so 50 to 150, is not an uncertainty, but depends on the way the trigger will be implemented, if either on the fluence and or on the peak flux. And in order to assess better this, we are now exploring with Giuseppe and Fabrizio in order to test how the implementation of real, let's say, simulated but resembling real-life curves could affect these numbers. In this plot here, as Fabrizio said, you can see the total population in black, the population that is revealed by, could be revealed by HERMES, and in yellow, the population revealed by the soft instrument. So thanks to the extension down to about 3 kV, it will be possible with respect to, for instance, a population like that of Fermi, having an access to relatively softer events, which are interesting for different reasons for a scientific point of view. Now, HERMES, of course, as was said also by Yuri, will have also interesting spectroscopic characteristic, and this could be exploited in order to study the issue I was describing before, because I hope I conveyed the message that this break is a new feature and can convey important information about the physical parameters in the emission region. So in order to evaluate these, we performed a set of simulation, and we basically calculated what is the minimum peak, the minimum flux a spectrum should have for a typical duration in order, and what is the corresponding peak energy in order to, let's say, reasonably well identify the break in the spectrum. So if you want, this is the limiting curve that we derived, and just to convince you that these are realistic, well, realistic but still simulations, here you see an example. So picking up a point close to this limit, you see the spectrum as should be observed by Theseus. The input spectrum here had a break at about 20 kV, a peak at 200 kV, and typical values for alpha 1 and alpha 2. Interestingly, you see that with this simulated spectrum, by reanalyzing it, we are able to derive relatively good constraints on both the slopes, alpha 1 and alpha 2, below the break and between the break and the peak, and the value of the peak and the break energy. You see that in these bidimensional plots. So the point here is that at least above this limiting line here, for the let's say the brightest part of the detected population, what is nice is that HERMES will be able to identify the break according to this simulation, but interestingly, it will be possible to track how the break evolves as a function of time, which is a very important point because it could tell us about the dynamical evolution also, which is present in the emission region, or other evolution of the parameters which are there. Now, it was said that HERMES could play, should play an important role in the game. No, it's not the correct word. In the study of gravitational waves counterparts. Now, this is a research topic that was boosted, of course, by the fantastic discovery in 2017 by the first gravitational wave produced by the merger of 2 neutron stars, with the discovery about 2 seconds after by the Fermi and integral of the associated short gamma ray burst, and few hours after of the kilonova. So the monitoring of this source over almost 2 years, and the precise localization in the sky and the study of its size and proper motion all contributed to set up a kind of a schematic picture, which I dare to reproduce in this plot here, where we think that after the merger, there was the formation of a compact object, which is probably powered by a disk and its rotation in producing a relativistic jet. This jet is, of course, piercing out of the environment, which is filled by this high-velocity ejecta, which is produced in the merger and pre-merger phase. So what comes out and what is interesting for us is the fact that the production of this kind of system is a jet with an angular structure, meaning that the energy within the jet decays as a function of the angle from the jet axis, as well as the bulk clearance factor. And the combination of these two ingredients, energy and bulk clearance factor, are fundamental, coupled to the Lune angle, to determine what we see and how bright the source we observe is. In fact, it is a kind of a matter of orientation. What does it mean? It means that this kind of source...
Giancarlo, sorry, you have 1 minute left.
Okay, and I have one slide more. Perfect. So if we look to this source close to the jet axis, we should observe a powerful GRB and a loud gravitational wave. And of course, as we move outwards, I mean, at larger viewing angles, we should observe different emission components dominating. If you want, in this plot, what I represent is the fact that if I take the jet of 170817 at 40 megaparsec, I see that if I look that close to the jet, which of course, however, is very unlikely because of orientation probability argument, I would see a very bright event. And for instance, at the angle at which it was observed, this event, with respect to the Hermes instrumental limit, we would observe it quite at the limit. So with this, you understand that we have a kind of interplay of the orientation, which determines the gravitational and electromagnetic ranges, meaning that in the close-by universe, more off-axis events are easily detected, but as you go at farther distances, of course, you are going to pick up events which are more or less more aligned along the line of sight. So by combining these ingredients into a kind of first attempt of a preliminary estimates, what we have is that as a function of redshift, Hermes is going, of course, to select, going at larger distances, of course, closer and closer to the line of sight, so more aligned jet, because these are more luminous, and therefore they are detectable at larger distances. So this is the line here. By combining these with the BNS detection, BNS merger rate, as derived by the recent second catalog of the LBC collaboration, we can envisage that this is the, let's say, cumulative detection rate of electromagnetic counterparts produced by BNS merger by Hermes itself, with this uncertainty, of course. And this is very promising because with the, let's say, enlargement of the horizon with the design, advanced LIGO, and maybe even something more with the next generation, of course, more with the third generation detectors, we will be able to catch these counterparts thanks to the sensitivity of Hermes. Now, these are preliminary results, and this will be refined with better detector responses, and okay, but these are details. And these are my conclusions, split into two parts: prompt emission GRB spectra. I think we came to a point in which it's clear might be the leading emission process shaping the spectral shape of GRBs, and this is very interesting. It leaves open some questions. We might find some solutions, for instance, changing the emission, the particles responsible for the emission. And Hermes is very promising for studying GRBs with these detection rates, can identify the break and its evolution, and can detect GRB counterparts, sorry, gravitational wave counterparts. That's a mistake. I'm done.
Okay, thank you, Giancarlo. And we have a question, I see in the chat, so please unmute yourself and